experts on tensor decompositions. It's also like a personal honor for me because she has been my longtime mentor at San Diego National Labs, and she gives amazing talks. So I think you'll all enjoy learning about large-scale tensor decomposition.
Thanks, Sesh. So yeah, thanks to Sesh and the organizers for inviting me. It's a great pleasure to be here. I've already learned a lot. And so I'll talk to you today from a little bit of an outsider perspective. And so I encourage you to ask questions if anything is unclear and kind of maybe go like this, like, yeah, we know it. So, so I'm going to talk about randomized least squares optimization and its sort of incredible utility for large-scale tensor decomposition. So one of the things I want you to take away is there's a lot of interesting problems for sublinear algorithms in the realm of tensor decomposition. So I'll talk about one, but the sort of big message, if you can go to sleep after this, is like think about tensor decompositions as a target for your research, and I would be happy to collaborate. This collaboration is with Brett Larson. He was a student intern when he started working with me at San Diego National Labs, and now he's at this place called, I think it's Mosaic Research. It's been bought up by Databricks. So, but anyways, he's still doing this kind of work with me. All right, so randomized least square, I'll just start there. So we want to solve some large-scale, highly overdetermined least squares system. I'm doing the matrix version, so I'm looking for a matrix X, and on my right-hand side is a matrix instead of just a vector. And then I have these dashed lines to say this is very, very tall. I'm using a big N for the size. So big N is the baddie. We don't want anything to do with big N. That's the thing we want to be sublinear in. And so the standard way to solve this would be a QR decomposition, and the cost is NR squared for the QR decomposition. And then because it's multiple right-hand sides, there's also a factor of NRM. In tensors, the M is usually bigger than the R. Doesn't really matter. Just think NR squared. And so what we want to do is just pick a subset of the equations and then solve that system. So the question is, can we do that? And so the basic idea here, so there's various types of sketching. You can multiply by a sketching matrix. We're going to do the kind where you instead actually very sort of almost a tailored picking of the rows you're going to use. And so you're going to select the rows of A and B with replacement. And then for each row, you'll have some probability p sub I of choosing that row. And the probabilities just add up to 1. And then you weight things accordingly. So that expectation, your sketch system has the same norm as your original system. All right, so questions you might ask, how do we choose the probabilities p sub I? So a lot of the talk will focus on that. There's the way that you could do it idealistically, which is very expensive. And there's a way that we'll do it in the specific case of tensors. And then how accurate is the solution of the sketch problem? And then how many samples do you need? Of course, those three questions are intermingled. What you need to know about is these awful things called leverage scores. They're very counterintuitive, the way they come up and why you need this weird orthonormal matrix. If you go through all the proofs and everything, you can uncover it. But I'm just going to tell you what it is. You don't have to accept the definition. You have some original matrix A that's n by r. In the context of least squares, its leverage scores, you have to find an orthogonal basis for the column space of A. And then you take that orthogonal basis, and the leverage score of row I of this matrix is the 2 norm of the row I of this Q. So the columns have norm 1, but the rows have norm less than 1. So you have one of those for every single row in your matrix. The best way to get a Q is like a QR decomposition or an SVD. That's big N R squared cost. So you've lost if you pay that price. But these are just sort of idealized things. And then just some facts, the leverage scores add up to R. So that's how you're going to normalize to get them to sum to 1. The maximum leverage score is somewhere between R divided by N. So that means everybody's exactly equal, or 1. If everyone's equal or close to it, then we say our matrix A is incoherent. Incoherent matrices are great because it turns out then you can just pick rows uniformly at random, and your life is very nice. In practice, most matrices are not incoherent. And so your choice is to either pick things smartly or multiply your matrix by something to make it incoherent. So one magic thing you can do is multiply by a random Gaussian. That'll make things incoherent, very expensive to do. We don't want to do that. There are other things you can do. I have other works on that, and I can talk about it offline. I don't want to talk about that today. Today, I want to talk about picking specific rows. And so the best probability we can use is proportional to the leverage score, just normalized so that they sum to 1. So that's the ideal. And then the theory that you get is that you have some original system you want to solve, and then you have your sampled system. If you take the solution from the sampled system, you plug it back into the original system, then you know that's within 1 plus epsilon of the very best possible minimizer in terms of the residual that you get, with some probability greater than 1 minus delta. And then your number of samples you need to make this true depends on the delta and the epsilon. And then the C, which is like a constant. I always need to know the constants. That's like 1679. Sesh will tell you I always need to know the constants. And then this thing, beta, which is a misestimation factor. I think we might have got that from David. So, hello. So it's the ratio of the probabilities you're using, or sort of a lower bound the ratios of probabilities you're using versus the best possible probabilities. And so what we want to do is make that as large as possible. 1 would be best, but then that would mean we have the perfect scores, but those are too expensive to compute. So we want to get that as big as possible. And then our number of samples depends on R divided by beta, and basically divided by epsilon. If epsilon is small enough, this term becomes insignificant. Any questions on that? And then, so I wanted to mention the second talk, and Shamali's talk today, number 2. So he talked about in stochastic gradient descent trying to focus on key elements. And so I think of this as trying to focus on key elements in the sketch system. So what are the most important rows? And so you can do something like a count sketch, but for reasons that we can maybe talk about in the discussion, that becomes very expensive because we want to actually avoid forming our matrix, which means that we then can't combine the rows with a count sketch. So I really like this idea of focusing in on the most important elements if you can figure out what they are. All right, so now I just talked to you about this problem least squares. We want to get this beta, and we want to be able to do these like approximate leverage scores very cheaply. So now let's switch gears and talk about large-scale tensor factorization. So how many people have seen tensor factorization before? I know, yeah, you talked about it. Yeah. So not that many. So feel free to jump in with questions. I am the world's a world-leading expert on this. So tensors come from many applications, and actually the people who apply tensors are much more creative than me. I'm like kind of fascinated by how much they've taken off. When I started working on them, I think computers weren't big enough to do stuff. Like I started just as they were getting big enough, and now I'm sort of just shocked by how many papers about tensor decompositions there are. So these are just some of the application areas that I'm familiar with or my colleagues have worked on and told me about. Really oddly, this was very popular in chemometrics for fluorescence spectroscopy. There's tons of really mathy papers in that literature in like the 1990s and early 2000s that could have easily been published in a math journal, even like NeurIPS. I think these would have been great papers, but nobody knew about this, but they were using it because it's very applied and useful. So it has a great history of being useful, and the best analog is principal component analysis. So this is this tool that is very, very handy for doing all kinds of things and understanding your data in a wide spectrum of applications. You know, standard data science, but all kinds of other types of science as well. And that works on 2D data, so data in tables. If you have a sequence of tables, like under different scenarios or at different time points, that's a tensor. And so tensors are coming up a lot in applications. And like PCA, a lot of people use some sort of tensor analysis to cluster their data, just sort of interrogate it, just play with it in various ways, and then it becomes part of some official algorithm that they write a paper on or something. It's used quite a bit in practice. So I'm going to talk about something called the canonical polyadic tensor decomposition, or it could be the Cantor tensor decomposition, or the Perifect tensor decomposition. This thing was invented many times with many names, but it was called CP tensor decompositions. I have some three-way tensor, size n1 by n2 by n3. I'm just doing 3-way for simplicity. It could be 4-way, 5-way, 1,000-way. It happens. And we want to factorize it. What we're going to get out of the factorization is 3 matrices. And the way that we put them together to build up a model is we take the first column of A1, the first column of A2, the first column of A3. We do their 3-way outer product. So it's 3 vectors. That means the ijk entry of the result is the I entry of this vector, the j entry of this vector, the k entry of this vector multiplied together. And then you sum those up over all the pieces, and that gives you the ijk entry of the model. So that's what that says. You don't really need to know that for the rest of the talk to make sense. That we won't even come back to that. But just know that there are 3 matrices, and then we're trying to minimize some error, which in this case is the 2-norm error between the model and the data. And then you pick some rank. That's how many columns are in each of these matrices. All right, so the motivating example I'll give you is to do analysis of this large-scale tensor Reddit. It's, I didn't even know what Reddit was when I started this project. My collaborator kind of explained it to me. And I use it now since Twitter kind of went away. So this tensor someone else put together in this formidable repository of sparse tensors and tools, Frost. So it's built with comments posted in the year 2015. And there's some pre-processing, but it has 8 million users, 200,000 subreddits, 800 words, so 4.7 billion entries where there's some combination of a non-zero user, subreddit, and word. So we don't want to spend time on zeros. We heard that in the last talk. And so the ijk entry of the tensor is log of 1 plus the number of times user I used word j in subreddit k. And so if we store this, we store all the non-zeros and the indices, and we're using like 64 bits each. I think we're storing everything as doubles. And we compute a rank. That takes 106 gigabytes to store. And then we want to do a rank 25 decomposition. So we could do some tricks to make the storage a little bit smaller, but it doesn't change the sort of bigness of the problem overall. So just to show you what we get when we decompose this. So we did 25 components, and here's how they drop off in magnitude, so the overall size of the component. They describe only about 6% of what we see in this tensor. Question? Absolutely. Oh, that's an art. Yeah, so as you increase the number of components, you get more of your variance explained. But at some point, you're fitting noise or something like that. And so you maybe, it's a judgment call. A lot of the problems, we can actually look at the factors and see if they make sense and how much they explain. And as they explain more, you might say, no, that's now too much. It's explaining too much detail. But that's one of the main open questions. And even for exact rank, for like a noise-free tensor, it's actually NP hard to determine the rank. These are fun problems. Yeah. All right, but I just picked 25 here out of thin air. So other people have done other ranks. So what we get is these vectors kind of give a ranking. So the terms, the words, and the people, the users. So we have some ranking. And so what we've done here is we've color-coded what subreddits get the highest score for this 6th component. And they're it's really, you can't read that at all, but it's color-coded by the frequency of postings overall in the whole data set. So this one is Ask Reddit, which is where the vast majority of discussions take place on Reddit, at least in 2015. And so that's almost brown. That's at the very top. Everybody else is shades of blue, so they get very little overall traffic. And then more interesting is the words. So the red words are pretty frequent, but the blue and green words are more interesting. So this is the word country. This is the word world. And the top subreddit is world news. So you see kind of themes emerging here. And so just to show you a couple more, this one is about relationships. The top subreddit is relationship, then relationship advice. And you have things like relationship, friend, tell, talk, someone. So relationship words. This is sports. We have NBA, NFL, team, player, fan. And then we have soccer. So if you are a soccer fan, there's like soccer, Red Devils, Gunners, FIFA, player, team, league, goal, fan, club, and then this one is computer card game. Maybe it's Hearthstone. I don't know if that's computer card game or a card game. There's like card deck, turn, player. So it finds stuff. This is sort of boring. I don't like the way this data was pre-processed. And you would never do it this way now, right? But it just sort of gives a flavor of what's going on. All right, so that's a large scale problem. And then to solve these, to fit these models, we do one method that people use is alternating least squares. And so the basic idea is we're going to solve for one of the three factors and keep the others fixed. And this ends up giving us a least squares problem with special structure. The factor we're solving for is our unknown. And then we have our design matrix here. And then the tensor, the data tensor, turns out like its entries are rearranged into that right-hand side matrix. And then we do this for the first matrix, the second matrix, the third matrix. Then we start again. So we solve lots and lots and lots, dozens and dozens and dozens of these least squares problem, 3 per outer iteration. And then this thing is called a Cottrell product. So that's what ends up being special to get some good, to get our good estimate. So all you have to remember is we're doing least squares problems over and over and over again. And then just to give you an idea of how much doing the leverage score sampling with an approximate leverage score helps is if we run on that tensor with 4.7 billion non-zeros. This is just in MATLAB on a computer with a lot of memory. It took like 96 hours per run for the usual method. And then with the randomized method, it's down to 8 hours per run. And most of that time is fetching the elements we need from memory. I am going to show you that. Oh, let's see. So in this case, I think it's these two. Oh, no, it's going through all of them. So it's 2 of these. It's like these two, and those 2, and then cycling through. So I'm going to show you that next slide. But the n is 2 of the sizes. And then we're cycling through a bunch of these problems. And then we use 2 to the 17 samples per solve. And that was just sort of done heuristically, but then later we kind of got the theory worked out. And it's like pretty close to what theory says we would need. All right, so this problem has structure. And so that's the main thing that's really nice and makes these things amenable. So this design matrix has this Cottrell product structure. And this would normally cost big N times R if you form this explicitly. So one of the games we want to play is we don't want to actually form this. That would be too expensive, which means we really can't do any kind of thing. Even like I think count sketch would be too expensive. And when we've done other types of sketching, we actually sketch these matrices. We probably could do that with count sketch individually and then combine them. If this thing is the reshaped tensor, if that's sparse, we can play special games to get the cost down to the R times the number of non-zeros, but that's still 1.2 billion. So we can make it a little cheaper for sparse, but we want to go even cheaper than that. So the comparison I was showing you was using the sparse method. And then for mode 3, n is equal to 1.2 billion. That's the special is this Cottrell product structure. So here we have, this is the Cottrell of matrices A2 and A1. And so what this means is that the kth row of this design matrix takes a row from A1 and a row from A2 and combines it. And so every row in here is all possible combinations of the rows in there. That's why there's N1 times N2. Sometimes Cottrell is called the column-wise Kronecker product. I don't know if that helps with understanding it or not. And then just note there's a one-to-one mapping. For every K, there's a unique IJ that maps into that. And so that's the structure that's useful. And the reason it's useful is this result that the leverage score of row K of A is bounded above by the leverage score of row I of A1 and row J of A2. And so from that, you can get a lot of nice stuff. Yes?
Relationship known to be tight. Like, is that the best kind of dependency you can hope for?
I think it is. I think there's an I'd have to double check, but I think there's an example. But don't 100% believe me on
I
that.
guess if A1 is equal to A2, then probably should probably be type, right? Because I mean,
I'm pretty sure we have there's an example, either we have or someone else has, that shows it's tight, but I don't remember well enough to say. Because this result was even earlier when people were doing a sort of a fast Kronecker type transform, fast Johnson-Linus-Strauss transform on it. All right, so this is expensive to calculate, but this is really cheap. So you could think of these n's, little n's, as being like square root of big N. And the other thing is when you have, this is for three-way tensors. If you have a four-way tensor, then there's three of these matrices here. And this is sort of like n cubed versus n. So that as you get higher order tensors, this is how many dimensions it has, it becomes more and more advantageous to do these sampling type techniques.
so you're assuming you can do QR decompositions of A1, A2,
Yes. Yep. And even like, with this 100,000 size, or maybe it was 1 million, you can do it in MATLAB. I mean, that's like nothing. But if it was, there are randomized techniques for those too, yeah. And so now our approximate leverage score we'll use is the product of the two leverage scores from the submatrices, and then we have to normalize by r squared to get everything to sum to 1. So what does that mean for that theory I showed you before? We can set beta to 1 over r. And then this means that our number of samples we need is proportional to r squared over epsilon. And so the best would be r over epsilon if beta was 1. And then for a general d-way tensor, it would be r to the d minus 1 here.
why do you get beta equal to 1 over r?
I didn't tell you. Yes.
Some of the linear dependence on 1 over delta, it's not what I would have expected. It seems a little large. Does that definitely need to be there? Delta's the failure probability?
Yeah. I mean, we usually set it to like 0.99, so it's.
Or 0.01, I mean, the failure.
Oh, delta's the failure, right.
So like 1 over delta would be 100 or something.
Yes. Oh, yeah. That's a good question. I have to double check if it has to be there. Yep. I wonder if I have it. No, I don't think I have it backwards. Yeah. Log. I don't have to double check. All right. So there's a couple of practical considerations. So I never want to actually form this matrix, and I don't want to form all these probabilities. I would have to make big N of them, and I lose my game of never doing anything big N. So instead, we choose a row I from A1 proportional to its leverage score, a row J from A2 proportional to its leverage score, and then we can form just that row in our sketched version for a cost of just multiplying those two together. It's a cost of R. And so that's one thing to do, and so that's a cheap way to pull out a row. Oops. And then the other thing is there's a couple of things that happen in practice, and this will be a panel on this later. And this turned out to be really important for us, and sort of something that I think is both trivial and very interesting. So what we saw in practice was that there might be some, I'm going to say heavy hitter because it was in a talk earlier, some heavy hitter row that when you sample without replacement, you keep seeing that heavy hitter over and over again. And it's normally not one, it's like a small number, but you get the idea. And so this gummed up the works in a couple of ways. One, you just had this overly big problem. It's silly in linear algebra to repeat the same row over and over again. So at a minimum, for basically no cost, you just do a little pre-processing and combine repeated rows. This is very simple. It's just a matter of reweighting that row to like sort of say how many times it appeared. And so that's like a freebie. You just do it, and that just by itself saves you like up to 20x on some of the problems we ran. So definitely just do that. That's not even debate. Like there's no reason not to do it. And then the more maybe interesting thing is to, I think we just heard this in the talk, a version of this in the talk earlier, pull out this row from your sampling and just include it. You're going to include it hundreds of times. Just go ahead and just include it once, and then just sample among the remainder. And the advantage of that is if you set some sampling budget, if it's all clogged up with a bunch of repeats of this red, you're kind of wasting your budget. So if you just use your budget to get more diversity of the remaining rows, that's better. Now, we are not forming these rows explicitly. We're not forming the probabilities explicitly, which is this like complicated rejection sampling. But that's still really cheap compared to actually forming everything. Our most expensive operation is going and pulling the data to construct this matrix. So we have to pool pieces, multiply it together, and with these really big problems, that's all the time is memory access. And so this was not easy to get through, and I think sometimes when people aren't experts in the theory, they don't understand the proofs, it's really hard to make this stuff work in practice. This would be sort of a practical thing. Question?
Do you have a sense in practice of how far the product of the scores is from the idealized score?
It can be pretty far, actually, yeah. And there, I'll say at the end, there's a recent work which does some kind of clever thing, like it picks one and then it and then it kind of modifies things to pick the next. It's just really expensive to do in practice. So you can sort of make it win under like specific scenarios, like this done by a group here at Berkeley. And it's really nice, but it doesn't, it's kind of expensive and hard to do efficiently. But yeah, I think there's room for improvement there. And then also say here you have to calculate who these big guys are. You don't want to calculate that explicitly, but you can use some tricks to try and find that. Great. And then, so for numerical results, so just to look at that hybrid sampling where I pull out the big rows, this is a problem with big N is 46 million. The R, the number of columns, is 10, and the number of right-hand sides is 183. If we just do the random, we kind of get convergence like this in terms of our number of samples and our error. And so we do this hybrid sampling, we're getting more diversity in our samples. So it's kind of effectively giving us a bigger sample size, but for the same space budget. And then we see that we converge better. We don't actually have great analysis of that. Like I think the beta should be better in that case. So that's one open problem I'll throw out there.
In this case, how did you calculate up? Like that's very expensive, right?
This problem was small enough so we could actually calculate it. Yep, great question. Yep. That is the.
Sometimes you wouldn't even know if you're approaching up, right? Like let's say some of the randomization went wrong. Like you wouldn't even know if you're converging to something bad.
I mean, you can plug it back in if you're willing to pay that cost. But yeah. And you can, yeah, you'll see some of the examples. I mean, you generally don't know, no, but yeah. So here's going back to that example for Reddit. And I maybe didn't say before, we did a bunch of runs. You always do multiple runs. So one thing is you kind of see whoever gets best and do they kind of converge to the same thing. And then I'll also note that the randomized algorithm is jiggy-jaggy. People don't necessarily like that. And you have to sort of, I don't know, make up a heuristic for when to stop. That's the trickiest thing. But it gets there very fast, even with these tricky conditions. And then just for fun, here's another tensor, which has no interpretation. They just put out a big tensor. But it is 8 hours to run. And then the randomized algorithms get 40 minutes or 47 minutes. And this, I didn't stress that things are sublinear, but there's no dependence on big N in our number of samples. That's sort of the big key. And then I mentioned before, this group at Berkeley has been doing some stuff where they can do this very specialized sampling where they use exact leverage scores, but they kind of compute them on the fly. So if you're a really good programmer and very clever, you can get this to work under some circumstances. But they're like doing a parallel version, and they told me they just went back to the other version because this was kind of too hard. Their fancy version was great, but too hard to parallelize. So there's like different options for people depending on your situation. And so today I'll just sort of end here and say that we looked at overdetermined least squares kernel. In the case of tensors, there's great structure. And you get, this 10x performance improvement. This is always, I say, I don't want to talk about anything that's going to yield 10x improvement. And normally you start thinking it will yield 10x. In the end, you get like 2x, and you still call it a victory. But this really gave sort of a 10x improvement. The practical considerations were really important. And I think this is where there's a lot of interest in like how to get these methods used in practice, addressing some of these practical considerations when they come up. And then the analysis of that hybrid method is still an open problem. So I would be very interested if anybody wanted to take that on. And then the reference for that is there. But I just want to stress there's many other problems. So there's all kinds of different decompositions. We did CP. There's something called Tucker. And then my artist illustration of this thing called Tucker train, which is for D-way tensor. So that's why I don't have a picture of that tensor there. There's other objective functions where we normally use stochastic gradient descent. So I'm really interested in better techniques for that. There's other algorithms that are of interest. So randomized range finding, stochastic gradient descent, semi-definite programming actually comes up in some tensor eigenvalue problems. And then there's structure. So sparsity, incomplete data, symmetry. I saw a mention of polynomials earlier. So polynomials have relationships to tensors. That's really fascinating. Symmetric tensors. You can have low rankedness in some of your other objects and so on. So there's all these pieces. And then I'll close with the pointer to the paper. I'm about to put up a book that's going to be published by Cambridge, but they gave us permission to put the entire PDF online for free. So that should be up, actually, hopefully within 2 weeks. And then if you want to get notified when we post it, it's there. So this is a textbook aimed at graduate students. And it has backgrounds in linear algebra and optimization and probability statistics as appendices. So it's kind of hopefully accessible to a broad variety of students. And I'm also working on a book, that's sort of a side project on using TIXI, PGF, and PGF plots for making LaTeX graphics. And I'm not going to name any names, but I saw some very small axis tick labels in this talk, so you should buy my book. Thanks.
Instead of using leverage squares, you just use squared root numbers.
Yeah, so the question is if you, can you use squared row norm? So we did an experiment on that, and you do see a difference. They're not bad, but there is a difference. And probably you could cook up an example where it was terrible, but it was actually surprisingly good.
No question. Do you have situations where you actually have to like stream the tensor? Like if you had a streaming algorithm where maybe, I don't know, you load it row by row, would that be useful? Because then the memory footprint would be lower.
Yeah, there's a lot of interest in streaming tensor decomposition. In fact, there's almost too many different ways to do streaming tensor decomposition. So I have like, I thought of doing it. I maybe did like one paper, but then I didn't know what problem to solve. There's too many different problems. So if there's like a good scenario, then there's a lot of ways to tackle it. And there's been some really nice papers. Like there's a really nice paper on streaming Tucker decomposition that I would recommend.
Any other questions? Yes, thanks.